Very excited to welcome Yubei Chen, an assistant professor at UC Davis. He will give us a talk on using generative AI models to improve generative AI models.
It's a great pleasure to be here today. And today I'm going to talk about very simple but quite useful ideas. By using generative models, we can improve the generative models. Over the past few years, there has been a tremendous progress in generative models, and which attracts the attention from all over the world. And this is a collaborative project between UC Berkeley, University of Oxford, Harvard, CMU, and UC Davis. So these generative models are trained on vast quantity of data at scale. And after these models have learned about these data, and they show some emergent generalization abilities. And today I'll be focusing on these diffusion models, but the ideas would be able to generalize to other types of the models as well. So as you can see that after you use a few photos of this particular dog, you can fine tune your diffusion models, and then it will generalize to different background and different activities of this particular object. So because the data is very limited in this scenario, and you don't fully fine-tune the whole model, but instead you only tune that, you keep the text encoder and image decoder fixed, and you only tune that UNet in between, right? Which turns that instruction into a latent space of the image space. But you can generate different settings for these particular objects. So another quite similar idea, use a bit better regularization, right? Rather than fine-tune that UNet, you only tune a very small subset of the parameters so that it has a better generalization. As you can see, that I start to learn even more abstract concept like moongate in a snowy ice, which is quite interesting. What we are interested in is that can we test how closely these models can actually follow our instruction and generate the scene that precisely matched our prompt. In this particular case, we wanted to generate a very precise composition of these objects. Here we have one dog, and we have a particular cat, and we want to generate the combination of these two objects in the same scene. As you can see that when we use the Dream Boost, the generated image is not quite, right? So there are three dogs rather than a dog and a particular cat, right? So there's no cat in this case. And the other images are similar, and these are two dogs, another two dogs. Custom diffusion, it used a bit better regularization, so it has a bit better generalization. But as you can see that here's the dog. Well, it's a cat-ish dog, and also another cat, right? So not quite, right? So, but more generally, we can also ask the diffusion models to generate images like, say, generic dog and a cat playing together, and that's a result from these models. And as you can see that it doesn't really follow your instruction quite well. And here's the stable diffusion 1.5, and we want a dog and a cat, a teddy bear and a bag. As you can see that here's a bag, and a cat, a teddy bear, but the dog is missing. And in the second example, it generates well, it fuses the dog and the teddy bear. The bag is missing, and there's a cat. So this model really cannot follow your instruction precisely. And rather than introduce additional regularization due to the limitation of the data, we want to take almost opposite direction, which really is a data-centric, right? But before that, let's look into the training data we have in these models. In these examples come from the line data set. As you can see, for each of these examples, there's a quite bit misalignment between the text and the image in the data set. Please take a moment to look at these examples. As you can see that this is an image, but somehow it's a jigsaw puzzle, right? Here, the description is also quite off. These cases are very pervasive in these data sets, right? So the question is, how can we get high quality data with precise caption at scale in a smart fashion? Can we scale our data in a smart fashion, right? So what we propose to do in this particular case is that we want to use generative models to work together and create our high quality data. And as you can see that we have different objects and we want to compose and get these different configuration and precise composition of these objects. And after we create this data set, maybe we can use this data set to further fine-tune our generative model to improve the composition and precise instruction following ability. And here's how we do it. So that's the goal, right? So you have a cat, you'll have a line, right? So you want to create a scene with a detailed caption in and compose them together. And how do we do that? The first step is that we are going to extract the cat and extract the line in this particular case, and also the mask. And in step 2, we're going to use a language model to compose these two objects, right? So, and propose the composition map for these two objects because they are different sizes, right? So we want to make sure that when we compose them, it's in a reasonable configuration, right? So not a tiny line and a big cat, right? So in this particular case, and further, we also want to use the language model to propose a reasonable scene for these two objects to co-occur together, right? So after we have this scene, and then we can compose this background with our objects together and use a generative model to generate this image. And finally, we can use language model or visual language model to create a very precise caption for this particular combination. So let's look at this pipeline again, and to make sure that everyone is on the same page. First, that we have different objects. We are going to extract these objects from this background. And second, we are going to use a large language model to find a reasonable combination proposal for these different objects. And then also use the large language model to propose a scene. And the combination of this object and the scene is not going to be a cut and paste because that would not give you a very natural, that would not follow the natural regularity of the images. But instead, we are going to use the diffusion models to do the inpainting and create this combination. And finally, we can use language model or large visual language models to create a precise caption. And along the way, we used many different models to work together, right? So the first one is the DIS, is CCB 2022. And the second one, for the language model, we use the ChatGPT API. And for the generative model, we use the Stable Diffusion XL. And for the visual language model, we use the Lava. This is almost a distillation 2.0. In distillation 1.0, where you have a big model and you try to distill the task of ability of this big model into a small model. But here, instead of having one model, we use a set of different foundation models and cascading them and combine their basic abilities together and to enforce this ability, right? So this is really a combination of many different abilities together. So let's take a look of some of the examples from this generated data set. First is 3 cars, right? So and this is a composed scene of these 3 cars. As you can see that the finally generated model also have this reflection of the car on the wet background, wet ground, right? So it really follows some of the regularity in natural images. And here's the combination of this plant, teddy bear. What is this? It's a toy inkfish, I guess, in a garden setting. And here is another one, right? So you have this one rabbit on the in the playroom. There's a rabbit on the blue cushion, and there's another rabbit on the table. And here's a pillow on the wet chair, toy car on the floor, a woven basket, and a gray wall. This is the caption. It's very precise, bag of words-ish caption, right? So reflect the scene in a precise fashion. And here's another example, which is similar to this and also give you a precise combination and caption. Once you have these data sets, right? So, and you can use these generated data set with an emphasis on composition and precise caption to fine-tune our generative model to even further improve their ability. But before that, let's look at the baselines, right? So these are some of the baselines. You try to generate a close-up view of a cat and a lion hiding in the grass, right? So, and these the generated image of the from the original baseline is really off. The second one is a sunny autumn forest and statue, and what's that? It's another one on the ground nearby a chair, right? So the generated image is also quite off. The final one is also similar. But once you have these composition and precise caption dataset fine-tuned model, and as you can see that the model, the fine-tuned model is able to follow the instruction quite precisely. Not 100%, because you can still see that this line is heading in the grass back, back there, right? So the size is slightly off. Well, it should be small, but not this small probably. And then the detailed regularity of the image could still have some artifacts. But as you can see, it has a tremendous improvement compared to the baseline method. So this is using generative model to improve generative models. But if you can do so, you can use the same idea to improve almost any model. Now, here's a couple examples. Is the first one is that from the simulator, if you have a simulator, driving simulator, you can use the generative model to turn that from the simulator to the real scene. And in anomaly detection, it probably is hard to find a lot of these defect example. But let's say you have some of these defects and some of the normal setting, and then you can use this generative model to fuse them and synthesize a lot of these defects. And further, in the audio setting, if you may have collected 1,000 to 10,000 different speakers and speech samples, and how can you make sure that this model is going to the real world and work with millions of users, right? So, and here you can use generative models to build virtual speakers and use the virtual speakers to combine even with the generative acoustic, room acoustic simulation to generate the real world data set, all with generative models. And this, by using a collection of these generative model tools, this is almost pointing towards the future of a data-centric AI, where we start to focus on the data rather than only on the model or the system. Right, just to summarize the key points of this talk, and first, we can use the generative models to be cascaded rather than before we have the one all-encompassing or omniscient model, generative model. We can still use a collection of different generative model and harness their basic abilities and cascade them to form our generative data pipeline. And then with the generative data, we can improve the generative models in return. And actually, that's a strategy has been used by DALL-E 3 and many other recent generative model in production. And because we can do that, and we can in return use this strategy to improve any model, this is the pointing towards a future of data-centric efficient AI. I think that's quite exciting future. And that really concludes my talk today. It's a very simple but powerful idea. And I hope this is useful. And any question for me?
Absolutely. Well, thank you very much for your talk. Excellent presentation, and appreciate the insights. Feel free to use the Q&A, everyone, as we get going here. One quick question from my side. Have you experimented You mentioned it can improve any model. I think that's one of the exciting takeaways you have here. Have you experimented with text to video examples as well? Outside of some of the examples you gave here, what's next in some of your quest on any model?
Yeah, so in fact, if we look at, let me try to go back. In fact, in each of these simple case, not in particular in this paper, we have a quantitative evaluation, particularly for improving the generative models at the title speaks. But this idea has been used to work on sim-to-real, defect synthesis, virtual speakers, and improve the speech recognition models, and it all works. And it can be with a very clear quantitative measurement. So I think that's, yeah, it has been used in
Awesome.
many different cases.
Awesome. And then this slide kind of alludes to it, but where are you seeing hotbeds or biggest areas of excitement in terms of the industrial or vertical specific applications? There's a few use cases here. I know you're on both sides. So where do you see some exciting breakthrough applications?
So I think that's a great question, and also I think that's the most exciting opportunity is that I believe that rather than have one foundation model takes it all, I feel that more the possible future is that we are going to leverage many different foundation models. This is almost, we can imagine a AI studio, right? So this almost like a Photoshop for each of the buttons, right? So each of the button is powered by a particular foundation model, and then you can start to have these different tools to work together and form your generative data pipeline to improve your task at hand, right? So rather to make a connection or analogy, this is like a multi-modality LangChain, right? So the LangChain, you can cascade different language models, but really you can combine different multi-modality models together.
Cool. Very cool. One question here we have is, can we use the concept of cascaded models to abstract proprietary information that corporations do not want to expose to the outside world through the normal LLM process? Interesting question.
Yeah, so I feel that to accomplish this task, maybe we are going to use not only generative model, but also the representation model. Generative models try to generate data, but representation model try to get the structure from the data so that you can use these model to select whatever the information you want to use and whatever the information you don't want to use, right? So, and then work together, right? So I think the representation model might be a better suited for this particular task.
Got it. And last question here before we go to our next speaker. I think it might refer to some specific slide or example you gave. The question is trivial, perhaps, but how did it, I'm assuming the model, infer the bear in the background?
I didn't hear this question clearly, so can you say the last part?
Sure. The question is, how did it infer the bear in the background? I think it refers to one of your specific examples or slides you gave.
Oh, yeah, that's yes. So that's a good question too. So when you have this dog, this pot, and this cat, right? So you send this into the language model and use the language model and tune on that API to find the reasonable background for these objects to co-occur, right? So when you have a dog and a cat and a plant, right? So what would be the reasonable background for them to appear together, right? So that language model is going to give you a proposal, and then you can use that proposal to either do a retrieval or to use your generative model to find that background, to synthesize that background. Sorry.
Awesome. Well, thank you very much. I think that concludes the talk here. Thank you very much, Yubei, for your insights. Your contact info is available through the website and your slides. A big thank you again to all of our sponsors that make this possible. In particular, thank you to the executive strategic partners of TinyML, Qualcomm AI, advancing AI research to make efficient AI ubiquitous. Also, Sentient, making edge AI a reality. The platinum strategic partners, EmbedUR, Sony AI to deploy Vision AI at the edge at scale. The gold strategic partners, ARM, Edge Impulse, Infineon, Renesas, ST Micro, and Synaptics. And the silver strategic partners, which we have here, AIZip, Arduino, BrainChip, bFission, Greenwaves, Gravity, IMAX, Imagimob, Initera, Noda AI, NXP, Procter & Gamble, Schneider Electric, SensiML, Silicon Labs, and TDK. So that concludes our first day. Don't forget, we have a lot more action-packed agenda for tomorrow as well, starting at the same time. So that concludes our session for today. And thank you for joining, everyone. See you tomorrow.